we're generally in the lower 50s right now and down in the lower 30s at night, but no snow at all yet. So
good deal. Do you want to share a screen? Is that how we want to do this
sure.
today?
Mm-hmm.
You have the button that should be at the bottom of the screen that says share.
Yep.
Go ahead and do that as you wish.
There we go.
And Carl has been a engineer, RF engineer for many, many years. He was with this company called Motorola for a long time and worked for Magnavox. So I guess he's made radios and TVs and maybe blenders. I'm not sure what else he's done.
No TVs or blenders.
No blenders.
Radios.
Okay, gotcha. That's good. That is good to know.
Yep.
Carl's with us earlier in the year and did a wonderful presentation on propagation. We're going to step back a little bit and do more about the basics of propagation. So if you're new or haven't been paying attention, this is the stuff that makes all our radios go. So Carl, I will pass this over to you, and I appreciate your time and efforts, and we'll see you on the other side. He has a hard out at 10:30, so that's why we're kind of pushing this up. So shut down when you wish, Carl.
Okay, very good. What I hope to go for 45 minutes and then have some questions and answers. So we'll see. I'm Carl, K9LA, up in Fort Wayne, Indiana. It's in the northeast corner of the state. We lived in the Dallas-Fort Worth area from 1979 to 1988. We moved back north. So very fond of winters down there where you can do stuff outside. And it's kind of nice. But yeah, last February, I gave a presentation on cycle 25 and space weather and propagation. And Mark invited me to do a little bit deeper. So that's what I'll do here. And of course, if there are other areas you'd like to hear more about, I'm usually available for those. Oops, how come it didn't work? I don't know. There we go. So first we'll talk about cycle 25, the latest data. That won't take long because I showed a lot of stuff back in February, which is still good. Propagation predictions, I thought I'd talk about them because that's a major understanding in propagation that I think can be confusing. Also, we have new sunspot numbers that can be confusing. And how do you interpret the propagation predictions, which are basically statistical in nature over a month's time frame? It's not, we don't have daily predictions yet. So the final bullet is what the bands sound like over a solar cycle, and also when there are disturbances to propagation. There's a heck of a lot more, and I just can't cover everything in 45 minutes or so. So here's cycle 25. So we've got about 9 more months of data since back in February. Cycle 25 is still ascending, but it may be slowing down. Now, cycle 25 is the thick red line there. I've also put 4 other solar cycles on that plot. The green one is cycle 24, which was our last one. It was the smallest in our lifetimes and the 4th smallest in recorded history. The next one up in orange is cycle 23. It's pretty much an average cycle. If you take the average of all 24, that's where cycle 23 is. The blue one's a moderately big solar cycle, cycle 21, which peaked in 1979. Gave us great propagation on the HF bands, on the higher HF bands, 15, 12, and 10, also on 6 meters. Unfortunately, not a lot of rigs back then had 6 meters. So boy, if we would have had those rigs back then, whew, would have been great. And that purple one is cycle 19, the largest in recorded history. And you can see it was a biggie. So what can we say from that plot? Well, cycle 25 is a little bit bigger than cycle 24. It may get up to an average cycle, like cycle 23, but we'll just have to wait and see what happens in the next 6 months or so. And it kind of looks like it's slowing down, so I'm not sure it's going to have any major increases, but who knows? The sun will do what it wants to do, not what we expect it to do. Okay, propagation predictions. Back in February, I mentioned that we don't have daily propagation predictions. What we have, as I just mentioned, was our predictions that are statistical in nature. In other words, probabilities, which that can confuse things. So what does that mean that we don't have daily propagation predictions? Well, it means if you plug in today's sunspot number, today's 10.7 centimeter solar flux, it may not necessarily tell you what the ionosphere is doing today. So you got to be careful. Now, why is that? Why don't we have daily predictions? Because there are three sources of variability of the ionosphere, and we only understand two of them. Solar radiation, we understand fairly well. We measure solar radiation via sunspots, 10.7 centimeter solar flux. That's in green because that's one of the ones I focused on back in February. And extreme ultraviolet, which is the true ionizing radiation for at least the F region. Sunspots and 10.7 centimeter solar flux are just proxies for the extreme ultraviolet radiation, which is very short wavelengths. One of the other sources of variability is geomagnetic field activity. That's when the Earth's magnetic field gets disturbed. We measure it with the K index. Again, it's in green because that was one of the ones to focus on from last February. The A index, which is a daily index. The B sub Z is how the interplanetary magnetic field from the sun is oriented with respects to the Earth's magnetic field, and also the solar wind speed. Higher speed, the more chance of a disturbance. But the third source, those are events in the lower atmosphere coupling up to the ionosphere. Even stuff down at ground level we can see in the ionosphere. It's not real big, but it can cause changes in the ionosphere. We don't have any parameters really yet to tie it to propagation. That's because it's still being studied to try and understand how an event down low can couple up to the ionosphere and what it does to the ionosphere. So that's why we have monthly median predictions, which are usually the maximum usable frequency and the signal strength. We just don't fully understand everything that goes into determining what the ionosphere is doing right now. Here's a good example of why we don't have daily predictions. All we have to do is go back to last month, October. Now, the orange curve is the daily sunspot number during October 2023. And you can see what happened. It decreased from about 150 in the first part of the month down to 50 in the last part of the month. So what did the daily maximum usable frequency over the Boulder ionoson do? That's the blue curve. It pretty much remained constant around 30 megahertz. So you can see why we would have trouble correlating a daily sunspot number to what the ionosphere is doing. And a simplistic explanation here is, as a solar cycle ascends, as it goes up, the ionosphere continues to build up. So just because the sunspot number goes down for a short period of time may have nothing to do with what the ionosphere is doing. So that's why we don't have daily predictions. Now, when we talk about sunspots, we've got to be aware that we have a new sunspot record. For many years, we used our old record. It's data from 1750 onward. Around 2010, their concern among solar scientists grew that this sunspot record was not accurate. So there were 4 sunspot number workshops held starting in 2011. Next one was 2012, 2013, then 2014. The end result was a new sunspot record. So to tell the difference, the old record is V1.0. The new record is V2.0. The major difference between those two records is a scaling factor that occurred way back when Alfred Wolfer took over from Rudolf Wolf in 1876 in counting sunspots. Alfred Wolfer had to multiply his numbers by 0.6 to agree with Rudolf Wolf's numbers. So that factor was carried on since 1876, and those sunspot number workshops determined that more than likely Rudolf Wolf was more accurate than Alfred Wolfer was more accurate, and Rudolf Wolf wasn't. So Alfred should not have multiplied his numbers by 0.6. And the new sunspot numbers were started to be reported on July 1st, 2015. Here's a comparison of the 2 sunspot records. In blue is the old data, version 1.0. In red is the new data, version 2.0. I only plotted it for cycles 19, 20, 21, 22, 23, and 24. And you can see that the new sunspots numbers are larger than the old sunspot numbers, and that can cause a problem, because how were our propagation predictions correlated between sunspots and the ionosphere? Well, they used the old record. So if you plug in the new record, you're going to have some optimistic predictions, which I guess that's better than having pessimistic predictions. But still, you got to watch and understand which sunspot record you want to use and which one you're looking at. So when you run a prediction in VOACAP or W6EL prop or online at the VOACAP, you should use a smooth sunspot number, as that is how the correlation was developed between sunspots and the ionosphere. And you should use the V1.0 numbers. So what you do is just take the V2.0 smooth spot number for the given month and multiply it by 0.6, and then you should get fairly accurate results with your predictions. Now, what comes out of the predictions are monthly median maximum usable frequencies and monthly median signal strength. Median implies a 50% probability. So on half the days of the month, the actual MUF and signal strength will be below the median. And on the other half days of the month, the MUF and signal strength will be above the median. Unfortunately, we don't know which days are the good ones and which days are the bad ones. So the best thing to do is just get on the air and see what's going on. Now, we can kind of summarize the median and the distribution about the median with a simple rule of thumb. On any day in the month, the MUF will be from 25% below to 15% above the median. Again, we don't know which days are good and which days are bad. And on any day in the month, the signal strength will be from several S units below to a couple S units above the median. So when we get those median values, just remember that over a month's time frame, the value on a real day could vary up or down. Now, I kind of talked about daily sunspot numbers and smooth sunspot numbers. Well, let's look at all three, the daily, the monthly mean, and the smooth. The daily sunspot number is exactly what it is. Every day, write down how many sunspots there were. And of course, Rudolf Wolf, way back when, came up with an equation to calculate the sunspot number based on the number of groups of sunspots and the total number of sunspots. So here in this plot is cycle 23. The red data is the daily sunspot number. You can see it's very spiky. In fact, it would be hard to determine what the sunspot cycle was doing. So the next logical step would be, well, okay, let's take all the daily numbers for a month and calculate the average. That's the monthly mean. That's the blue data. It's still kind of spiky, but you're starting to see that, hey, it looks like there might have been 2 peaks for cycle 23. So let's further average it. Let's do a 12-month running average of the monthly means. That's the green curve. You can see it takes out all those spikes, and it gives a really good picture of what the solar cycle did. There were 2 peaks for cycle 23. There were 2 peaks for 24. I don't think cycle 25 is going to have 2 peaks, but we'll see. And if you plotted the 10.7 centimeter solar flux, you'd see similar results. The daily results are spiky. Monthly mean is better. The smooth results give a, what can I say, a very smooth picture of what's going on. And there are 2 good reasons for using smooth values. One is, as you can see in this plot, it's a great way to see what a solar cycle is doing. And also, as I've mentioned before, the smooth value of sunspots or solar flux gives the best correlation between sunspots and what the ionosphere is doing. So there was a lot of method to the madness that was developed in the 60s and 70s when propagation predictions started to take place. Okay, what do the bands sound like? Okay, let's just take a look over a solar cycle. The lower bands, okay, I'm going to divide the bands up into 3 segments. One, the lower bands, 160, 80, 75, 60, and 40. If you operate a lot, you'll realize that they're best during the night around solar minimum. That's when there's the minimal amount of D region absorption. There still is some, but that's when it minimizes. Man-made noise and atmospheric noise are very critical on these bands. That's because of the D region absorption, the signals can be very near the noise level. The noise level being either your man-made noise in your area or atmospheric noise that propagates into your location. Big stations, you know, the 1.5 kilowatts with big antennas on the lower bands, they still have opportunities during the night around solar maximum. So it's not that the lower bands go away around solar maximum. It's just you may need a bigger station, which means more power, better receive capabilities, and also bigger antennas. Now, there's something that's interesting. Climate change may be detrimental to these bands. That's because as the CO2, carbon dioxide, increases in the atmosphere, that causes more electrons in the lower ionosphere. The lower ionosphere is the D region. More electrons down there cause more absorption. And that may be a reason or partial reason of why the lower bands just don't seem to be like they used to be 10, 20 years ago. Of course, you always have to realize that in addition to climate change, it may be due to more electrical devices causing more noise around the world. And that is very well documented. So the low bands are getting hit maybe by 2 things, unfortunately. The middle bands, 30, 20, 17, they're generally good throughout a solar cycle. I've heard lots of people say if you can only put up 1 antenna, put it up for 20 meters. That means you could get on all throughout a solar cycle, and you'll have a lot of fun. Generally, 30 meters is best during the night, and 17 is best during the day. But they hold up very well over an approximate 11-year period of a solar cycle. The higher bands, 15, 12, and 10. Well, they're best during the day around solar maximum due to increased ionization because, you know, as the solar cycle goes up, there's more extreme ultraviolet, and thus there's more ionization. And that increased ionization can give strong signals for modest stations. A modest station is maybe 100 watts and a dipole inverted V or a vertical. And those higher bands are also still good a couple hours after sunset. That's because when the sun goes down, the free electrons don't recombine very quickly with the with the positive ions. So the F2 region kind of gradually decreases. It's not a turns off at sunset and that's the whole story. Now around solar minimum on 15, 12, and 10, well, not many signals. All you're gonna mostly hear is noise, but I have to qualify that comment with the FT8 comment that's on the next slide. We'll get to that here at the bottom of the slide. What about 6 meters? Well, there are two major propagation modes on 6 meters. Of course, there's a lot more, but the two major ones are via the F2 region, and that's best during the day at solar maximum. And that's about where we are right now, even though it's a kind of a small cycle. There's still enough ionization for 10 meters. For 6 meters even, so I'm sure we're going to see some F2 region propagation during the fall and winter months. There's also sporadic E. That's best in the late morning and early evening in the summer months, June, July, and August. Also, there's a small possibility of a sporadic E in the early evening in December. So keep an eye out for F2 region propagation on 6 meters. 2 meters and higher, well, those bands are mostly line of sight. In other words, if you can see the station, you should be able to, if you can visually see the station, you should be able to see a propagation, line of sight propagation. Probably the next major mode on 2 meters and higher is tropospheric ducting. That can give strong signals over great distances. There are websites that predict when tropospheric ducting can occur. What I'm going to do with this presentation is make a PDF and send it to Mark. And I think I'll add a URL to that tropospheric ducting prediction website too. 2 meters and above are not affected very much by the sun or disturbances to propagation. In a way, that's good, but on the other hand, that means 2 meters and higher are pretty much just line of sight type bands. Of course, there's EME, which can certainly do more than line of sight, but for most people, it's line of sight. Now, my comment about FT8, on all the bands, FT8 offers more opportunities because signals below the noise can be decoded. So this last solar minimum probably will go down as the most activity on the higher bands because of FT8, and that was the only propagation mode that was working, or the only mode that was working. The ability to decode signals down in the noise is really significant. FT8 is reasonable in doing that. There are other waveforms that can decode even farther down than FT8. So, comments like 15, 12, and 10 aren't good at solar minimum may not be applicable anymore if you use some of the digital modes. That'll just keep us active and keep those bands active, so nobody gets any idea of taking them away from us. About disturbances to propagation. Well, there are three categories of disturbances. The first is geomagnetic storms. You've probably all heard of coronal mass ejections, CMEs, or a coronal hole. What those do is elevate the K-index. The K-index is a 3-hour index telling how active the Earth's magnetic field is. If the K-index is high, that could disturb the F2 region of the ionosphere. That's what that okay, it can reduce the high latitude MUF. The higher bands may not be available for several days because the MUF, the maximum usable frequency, has dropped below the higher bands. Here's a good example. August of 2011, I was looking at the ionosonde in Peru, and you can see what happened on August, towards the end of August 5th, the K index spiked up to 5 and 6 in red there. And the MUF over that ionosonde in Peru was kind of steady, or between 15 and 20 megahertz until the K index went up, and then it went down to 10 megahertz for a while, then came back up to normal. So high latitudes are probably most affected by a geomagnetic storm. In other words, the K index going up. Now, a geomagnetic storm can also give a short-term enhancement on the low and middle latitude paths. So what's a low latitude or middle latitude path? Might be Oklahoma to VKZL. That means the path stays pretty much at the lower latitudes, whether it's north lower latitude or south lower latitude. And here's an example on that same day at the ionosonde in Florida, Eglin Air Force Base. You can see when the K index went up to 5 and 6, the MUF spiked up for a short period of time, all the way above 10 meters. And then it settled down again. So, things can happen. Most of the time, a geomagnetic storm is bad. But if you're in the right place at the right time, you may catch an enhancement on a path. And of course, the VHF types like geomagnetic storms because they can offer VHF contacts via aurora. A second disturbance to propagation is what's called a solar radiation storm. That's due to relativistic protons. In other words, very high energy and high speed protons, almost the speed of light, that are generated by a big solar flare, generally a high M class or an X class flare. And what that does is causes increased absorption in the polar cap. What's the polar cap? That's the area inside the auroral zone. And that increased absorption degrades over the pole paths. And there's an example of an over the pole path. You can see the little red dot in the antenna in Oklahoma. It's close to Oklahoma. And there's a path over the pole, goes through the auroral zone and over the polar cap into deep Russia. And that path could be degraded. So most of the time we're not working those kinds of paths, so it's not much of a problem. And the solar radiation storms only last maybe several hours or so, and then it's back to normal. The third disturbance to propagation is a radio blackout. And that means exactly that. The bands go away. It's due to the X-ray radiation from a big solar flare. Again, big solar flare is a high M class or an X class. Causes increased absorption on the daylight side of Earth, and that causes more loss. And if the loss is enough, the whole band goes away. Now there's a picture from one of the predictions for how much loss is incurred when a big solar flare hits. You can see that orange area. The X is where the flare was overhead, coming from the sun. And you can see it affects a pretty wide area. The orange means that there's at least 1 dB absorption above 30 megahertz. As you move away from that overhead spot, of course, it gets less and less. The greenish says there's at least 1 dB absorption only on 20 megahertz or so. And of course, when you get to the blue area, okay, there's at least a dB absorption at 10 megahertz. So just remember that as you move farther away from the overhead point, the effect of that flare is diminished. Now, on the right side of that plot is the attenuation versus frequency. And what's very obvious is the lower bands are affected the most. They have the most absorption, whereas you get up to 10 meters, 28 megahertz, the absorption is not very much. Now, these generally last about an hour, so it happens, and then things come back kind of quickly. And it's probably the third worst disturbance propagation. Of course, geomagnetic storms are the worst because they can last for several days by decreasing disturbing the F2 region and decreasing the maximum usable frequency by a good amount. Okay. I certainly like to give you more details on what you'll hear on the bands, but unfortunately, we just don't understand everything yet, especially short-term events. We can't predict them, and it's great if you're sitting at the rig at the right time and you're on the right band and something happens interesting. We have to remember that the ionosphere is very dynamic. It varies in the short term in ways that we don't fully understand. We're trying to learn about it, but we're just not there yet. It can cause the MUF and the signal strength to go up and down, and the result of that could be QSB. Another cause of QSB is maybe a couple different modes, like a 1-hop mode or a 2-hop mode, could be propagating to the same place, and they could interfere or they could add. So expect to hear QSB on the bands. That's more the norm than anything. The ionosphere is not homogeneous throughout the whole world. You can divide the ionosphere up into 3 general areas. One is the equatorial ionosphere, the ionosphere around the equator, the mid-latitude ionosphere, and also the high latitude ionosphere. All 3 of these areas experience different processes, atmospheric and ionospheric processes. So it's hard to make a general statement, and we just can't do it yet. I think we know a lot, but we just don't know enough. And here's that bottom bullet is really what I truly believe. The best way to gain an overall understanding of the ionosphere and propagation is to read a lot. There are books and there are websites, and then get on the air a lot too. In my February presentation, I gave references, and here they are again. I did add a new one, the second bullet that's from the ARRL, here to there, radio wave propagation. All of these are very readable and not highly technical, so they're a good start. And of course, my website, I gotta mention that at least a little bit. So, summary. Understanding propagation is not a 24-hour effort. It takes a lot more than just 24 hours. Read as much as you can, books and websites. Get on the air as much as possible. One of the great ways is do a contest on a single band. For example, CQ Worldwide DXCW is coming up in, let's see, in 2 weekends, I guess. Wait a minute. Yeah, we're the 11th. Yeah, in 2 weekends. I've done the contest on a single band, like 15 meters or 12 meters, or 15 meters or 10 meters. And that's a great way to understand what the band does over a day, and even over 2 days, because just because it does this on Saturday doesn't mean it's going to do the same thing on Sunday. And of course, staying overnight at a Holiday Inn Express won't help much, but I've tried to claim that, but it hasn't gone very far. So Mark, that's all I had. If there are any questions, I'd be glad to answer them.
I very much appreciate all of that good stuff. And I did stay at a Holiday Inn Express last week, and you're right, it didn't help. Didn't help.
Oh, darn. Okay.
Well, I'm sure we'll have some questions here. I have one, and I'm afraid I know the answer from 3 slides ago, which is dynamic, and we don't know everything. But the thing that always spooks me is I'm on the radio, and all of a sudden the band just falls away, just like somebody unhooked an antenna. And then it may or may not come back. Is there any story there that can make me less crazy?
Well, I've noticed on packet cluster, I've seen lots of reports of radio blackouts, which means a big solar flare is causing some of the bands to go away. What band was this on? The higher bands?
Oh, there's 20, usually it's 20, 40, 20, somewhere in that range is when that will do those drops.
Well, that would happen. Yeah. It could be some geomagnetic field activity that causes the MUF to drop. And that would cause
just in an instant. I mean, it's some of, QSB is typically slow.
Yeah.
But it just nailed it, nails it. And it always spooks me.
Well, flares, geomagnetic storms, of course, those will affect absorption and those will affect the MUF. So that'd be a place to start, I think. There probably could be other things. There's a lot we just don't know. It's a very complicated system up there.
That's exactly what I was afraid of 3 slides ago when I saw that. But I always, when those happen, I always go look at my coax, and I know somebody's pinned my coax, and it's always me.
Hold on, let me look at something.
Your disclaimer, it says we don't know as much as we think we know.
No, you can see that. Okay, look at the top plot. You can see that MUF on a given day is going up and down, and there's some pretty sharp decreases. So if the MUF is okay, let's suppose the MUF was let's suppose it was August 5th. It looks like about noon. The MUF was 15 megahertz, so 20 meters would be okay. But then for a couple hours, the MUF dropped down to 10 megahertz, which says 20 meters probably would have gone away, and it would have went away pretty quick. So it's just the daily variation of the ionosphere can get you too, which may have nothing to do with geomagnetic field or a big flare.
Multiple causes. Multiple causes.
Multiple causes. Yeah.
Had a question on. Question is, an event like the Carrington event.
Yes.
Is that probable in this year, in next 2 years, 5 years? Any predictions on those, or is that just hold on, more to follow?
I've seen predictions. Eventually, we'll have another one. Yeah, I don't know if we could predict accurately how early it's going to happen. It's just like predictions for sunspot cycles. I'm aware of over 50 predictions for cycle 24. That's because we just don't understand the solar cycle process. So there's all kinds of methods developed to predict the solar cycle from way down low to very big, but most of them aren't correct. So all I'd say is we'll have another Carrington event someday. We may not be alive for that, but at least our generation may not be.
Yeah, I was kind of glad to see that the Alfred versus Rudolph fight was solved, because I think John Stratton went to college with one of those two guys, if I remember right. Is that?
I don't think so. I don't think so. Well, maybe. Yeah. Okay. Yeah, you're right. John is the director for the West
for Oklahoma, Texas. He's our guy. And
yeah, he's your guy. That's right.
We tease him as much as we can.
Okay, I'll have to.
Got a big laugh in the room. Hang on, we got another question coming your way.
Okay.
Bing NI5G. You mentioned something about FT8 and that there are some things better than FT8 that are out there. If you could say some more on that. And also, is there an app where we can trace the propagation like you just had on that last slide?
Let's see. You mean this slide? Or another one?
Yes.
Okay. Tell you what, I'll add, before I send this presentation, what I'll do is I'll add some digital mode data. Let me write this down so I don't forget. And also some websites where you can watch what's going on basically on a real-time basis. So you can see that, hey, 20 meters might be good, 10 meters should be good. And that'll give you an idea that maybe you ought to sit down at the radio. Okay.
Yeah, I've said many times, the best thing you can do is just sit there and listen for about 500 hours.
Yeah.
And you'll come away seeing all the stuff that can happen, and you'll still be confused, but it does give you a good idea what to listen for. And
yeah, you may not know what's
pops.
causing it, but hey, it happens. So I'm gonna.
I started back in the 80s when we had the woodpecker and all that other fun stuff happening, and it was what's that? I don't know.
Yeah.
Somebody always knew floating around. Anybody else have any questions here or online? The online folks, feel free to jump in and ask if you have some. Anybody in the building, in the room? Got one. Oops, we got one. We woke Ken up. Hold on.
Okay.
Okay,
Give me a call and your name.
this is Ken K5HFE. You made reference to climate change and carbon dioxide, and our carbon dioxide levels in the atmosphere are on the order of 0.04% today, and 200 years ago was 0.037 or 8, something like. I might be wrong on the numbers slightly, but it's very, very small amount. How profound an effect does that really have on propagation at those levels? Is that documented very well?
Well, I think it was back in. It was either recently or kind of recently. Some scientists did simulations of carbon dioxide levels in the year 2000 and what it's going to be in the year 2100. They assumed that the CO2 level is going to double. And what they showed is an increase in electrons down at lower altitudes. In other words, down in the D region and all that. They did, of course, they weren't hams, I don't believe. So they didn't correlate that to what that means. I've always threatened myself to try and do something with that, but I haven't done it yet. It should be kind of simple to estimate what happens when the CO2 level goes, doubles or whatever it is. And I don't know how accurate their assumption is that the CO2 level is going to double from 2000 to 2100, which of course we won't be around for that. But it doesn't take much to increase absorption to where the low bands have a problem. Now on the higher bands, there's a rule of law that absorption is inversely proportional to the square of the frequency. So as you go higher in frequency, absorption is less and less by quite a bit. So the climate change is, I only mentioned it in the lower bands because that's where it's going to be, it's where it's going to happen. And I don't know what else to say about it.
All right. Yeah, we appreciate that. Anybody else questions? Anybody else online? Anybody? All right, Mark, you want to?
Thank you very much, Carl. We appreciate your efforts in this, and complex topic it is. Thank you very much.
I mentioned earlier when I was giving the presentation earlier, I mentioned I was going to add something into the slides. Anybody remember what I said? Ah,
You're gonna add a digital, the digital representation for the,
Yeah,
the graph is,
and then real time.
And web.
Yeah, real time,
And
yeah.
web pages to go look at.
and the URLs for those.
Oh, for
For the
oh yeah.
digital,
Let me
digital.
go find out where that is here.
yeah.
Where was that? I remember that now.
It's the two graphs on the right-hand side that from Elgin and
Oh, okay. Eglin.
Eglin. Oh, I'm thinking of my good old days in Illinois.
Yeah,
man.
don't call it the Eglin
Elgin.
or Elgin Air Force Base. They wouldn't like that.
No. Elgin, Illinois wouldn't like
Yeah.
Eglin, Illinois either. There you go. That one.
All right. Yeah. Okay. There was something else I was gonna.
Hang on, Lyndall's got it. What do you think?
I could always add the URL where if you want to read about the new sunspot numbers too.
Yeah. Yeah,
I'll
I
let
think
you guys-
Adolph. Yeah, that's John's roommate. I think was Adolph. Yeah.
Yeah. Yeah, John's roommate. Yeah.
We've
They weren't John's kids, were they?
maybe we'll have to ask him.
Okay.
Oh, yeah, the books and stuff, the propagation.
Lyndall said something about reading books or books for propagation.
Okay.
There was a website there that you had listed. ARRL's new
Oh, on the
fourth edition
Oh, on the book. Yeah.
and
Yeah,
on
okay.
propagation, which is now out.
Yeah, that's that book that the ARRL just pulled out basically came from the chapters in the handbook and the antenna book.
Oh, really? Okay.
Yeah, so
That one is that the one you're talking about, Lyndall?
yeah, the second one down there, here to there, radio wave propagation. Yeah.
Didn't have any didn't have any links, and we're going to add some to it as well.
I should well, the ARRL bookstore.
Yeah,
That's
we can go back listen to the audio, and I'll send you a message if I see it.
okay. Yeah.
All right.
Yeah, there was something else earlier, but I'll look through it and I'll do a little bit of work on this presentation and send it to you.
We thank you very much.
Okay.
Thank you, sir.
We got a hand up. Hold on, we got one more.
Okay.
Mark, you want to grab Brent? One more.
Just,
Calling your name.
this is Brent Shambaugh, KI5CWB,
Okay.
and I was just wondering why the aurora seems so much bigger, and it's also kind of offset around Antarctica.
Well, it's because the Earth's magnetic field is always changing. It's not constant. It's the value is diminishing. One of these days, the magnetic field around the Earth's going to shift. That's going to screw up a lot of stuff, but that'll probably be way into the future. We won't be around for that, so that's good, I guess. You're probably aware that the North and South Pole are moving, and that's just because of how the molten iron inside the Earth is moving around. That's what causes our magnetic field, and it's just moving around, and we can see the difference there. The geomagnetic pole, which is different than just the simple north magnetic pole, is also moving. I have a slide showing that, so let me write down, and I'll put that in there too. Pole movement. It's just moving around, and that causes things to change.
My wife's an 8th grade science teacher, and she had a question last week that said, did we invent daylight savings time, or did the sun do that on its own?
Ah, yeah. Yep.
My wife didn't have an answer for that one, so I don't know. Maybe we can work on that for the next one.
What
but,
I've heard is it was invented so people could golf at night in the summer.
That's probably true. That's
That's
probably
probably
true.
a lot of truth to that too.
Yeah, it probably is, especially with the people that are voting to do that. So I'm guessing
Yes.
you're right. Yeah, I'm guessing you're right. Any other questions before we run or we take off? Carl, I appreciate your time. Thank you very much.
No
again.
problem, Mark.
Thank you,
Thanks.
Carl.
Thanks.
Okay.
All right, we're going to take a quick 5-minute break, and then we've got a pretty good meeting today. We got a lengthy meeting because we have elections today as well. So we'll have that in there. So take a quick 5-minute break and come back in here and we'll get started.